Hello and good afternoon to the European helicopter industry. My name's Scott Carmichael. I'm a consultant that works for Heli Offshore. Heli Offshore is a helicopter safety organisation, and it was created by the offshore helicopter operators, specifically looking at the improvement of safety in the offshore helicopter industry. Myself and Simon work in a project sector within Heli Offshore's safety performance model called the System Reliability and Resilience workstream. And that's essentially anything to do with maintenance, continuity, airworthiness, and design and reliability of the aircraft. Today we're going to present to you a kind of new approach. We think it's a new approach, but it's probably got some familiar aspects to it. Where we could start to look at taking the next step in safety improvement within maintenance by combining maintenance experience and design experience. We call it the human hazard analysis process, and we'll just walk you through it. I'll talk to some of the background of why we selected and developed this process, and Simon, who's the brains of the organisation, will go into some of the more scientific and technical aspects of it. So within our work, within the reliability and resilience workstream, we were looking at ways to what kind of initiatives we could take on to improve safety from a design perspective, certification perspective, maintenance or continuity airworthiness. What surprised us was there was many of the members of Heli Offshore kept grabbing myself and Simon at conferences like this and insisting that we address maintenance error as the primary safety concern within the industry. So we took it on and we had a look. We had a look at the data that is available around maintenance error, but we curiously found it difficult to find many examples of helicopter accidents where maintenance error was the primary cause. We did find many accidents where there was a technical cause that initiated the sequence of events that led to the accident. But we had to question ourselves because we found that many of those technical causes were perhaps not preventable through maintenance alone. Okay. However, so I have experience in maintenance and continuity airworthiness, and obviously I have a lot of colleagues and a lot of members that do as well. And we definitely thought that maintenance error, if we couldn't find many accidents that were a direct result of maintenance error, then why was maintenance error such a concern to our membership, which included both the operators and the customers? From my own experience as an engineer, I know that many errors do occur within maintenance during the practice of maintenance, so during the evening's line check, during the base check. There's many errors that do occur on a natural flow through the process. However, the system itself, the Part 145 system itself, is designed to capture errors as they occur. That's why we have functional checks, why we have duplicate inspections, why we have operational checks that follow the maintenance task of replacement, installation, or servicing. We also know this fundamental truth of the universe, maintenance engineers are very much the same as pilots in the industry. We take people when they're very young, and we all train them, and they have an institutionalized type training. So every maintenance engineer in Europe is trained to the exact same standard. Every pilot is trained to the exact same standard. And within that training is the right way to do things and the wrong way to do things. We also encourage maintenance and select people to become maintenance engineers who are naturally gifted and talented and very good at solving problems. The downside that comes with that is maintenance engineers make mistakes. Maintenance engineers find ways to overcome problems during maintenance, and they wouldn't necessarily recognize it as safety intelligence. What they would recognize is that job was really tough to do. I've just found a really good way of doing it, and I'm going to tell all my friends, which is perfect. However, it's kind of off-page safety intelligence. From the accidents that we did find that were directly attributable to some kind of maintenance error, both in fixed wing and rotorcraft, we discovered that a lot of the time it was an engineer who carried out a job, and he was the first engineer or the only engineer who didn't have the inside knowledge of how not to mess it up. You find that the rest of the shift or the rest of the industry never had that problem with that particular task, but this one guy did. But essentially all he was doing was making the same mistake that other people had made, but the organizational knowledge or the village speak had not got that information to him. So the question that we pose ourselves, so starting from the position that maintenance error is the highest risk to safety in the industry, but actually having conversations with people and looking at the records to say, well, it's something more than maintenance error. It's maintenance error that stems from what is normal practice, but that normal practice isn't documented anywhere. So the organisation is not able to get the benefit from it. We also thought if that normal practice that's emerged through the practice of maintenance could be somehow captured and fed back to the aircraft manufacturers, then the aircraft manufacturers may be able to develop designs of aircraft or designs of maintenance tasks that prevent the next generation of maintenance engineers from making the same mistake. Oh. So that's the question. So we did find one helicopter accident that we thought was a very good illustration of, and it helped focus our thoughts. This was a helicopter crash, or a helicopter accident that happened in the US. And when the investigators were inspecting the wreckage, they found this is a main servo control input rod. So it's just an eye end, a fork end, a bolt, a washer, stiff nut, and a split pin. And there were 3 of these installed on the aircraft. When the investigators were going through the wreckage, they discovered that that bolt was missing. And not only was the bolt missing, there was no evidence on the remaining parts that the bolt had fractured in service. So the only conclusion the investigation report could come to was that the engineers somehow forgot to fit a stiff nut and forgot to fit a split pin. Whereas you can understand both engineers absolutely claim that they did install it. So the accident investigation, for me, as a maintenance manager as well, it kind of made me angry because the recommendations were we need to train maintenance engineers in human factors, and we need to create more procedures for maintenance engineers, which is frustrating as an operator or a maintenance manager or for anybody in the room because it doesn't guarantee that the same thing won't happen somewhere else in the world. So what do we have? We have 2 professional engineers with years of experience, a bolt that is designed perfectly in accordance with the regulations. It has 2 independent means of locking, and somehow this bolt wasn't discovered at the crash site, and they can guarantee that it wasn't sheared. So where does that leave us? For us, for the rest of the industry, how can we take any lessons away from that? Also, you get angry as maintenance practitioners and say, how can 2 guys make such a terrible mistake? But if we also reflect that for the last 30 years, In the maintenance regime, we have been teaching maintenance engineers human factors. So we've essentially been training maintenance engineers for 30 years that you're a human being, regardless what we think. You are actually a human being, not a god. You will make mistakes. However, we create a design like this that the entire safety in the aircraft is based principally on an engineer assembling this nut and bolt and never making a mistake. So for the whole time that aircraft is in service, which could be 25 years, if there's 1,000 of them around the world and there's 12,000 engineers working on it, the whole basis of the safety of that aircraft is an engineer will never make a mistake, he'll never have a bad day, he'll never suffer from a human factors element, he'll never come to work tired, he'll never be doing it in the middle of the night. And that seems as if, to me, there's an opportunity there to rethink what we're doing. If we design aircraft and maintenance on aircraft with the assumption that a maintenance engineer never makes a mistake, but on the same time we're teaching maintenance engineers to be cautious because you will make mistakes, it seems a bit ironic. So I think what we were looking for was a way of trying to tap into the frontline maintenance engineers and give them a safe space where they can talk about, we know this is how the procedures say carry out this maintenance task, but what types of problems do you have when you're carrying out those tasks, and what kind of mistakes have you made in the past? So we're collecting that intelligence, but that's only half the story. The second half of the story is to get that intelligence and put it to use somewhere where it can benefit the entire industry. So what we do is we've created a process called the human hazard analysis process, where we hope to get to a point in the future on next design aircraft, but also on current design aircraft, where we can reduce the amount of human error or maintenance errors out there by designing the aircraft to actually support the maintenance engineer in his role. We've developed this process, and this is my cue to get off the stage and hand over to Simon.
Hi, everyone. I want to talk a bit about the actual process. How do we go about doing a human hazard analysis workshop? The origins of this are when there was a proposed change to JAR 25 at the time to incorporate the understanding of maintenance error into regulation. And this was an initiative kicked off by the UK CAA. Hazel Courtney, our colleague in this project, was at the CAA at the time. I was maintenance human factors manager at Airbus Fixed Wing, and I took up the challenge of coming up with a method, and we developed a mechanism to look at emerging design, looking at new design and incorporating human factors into emerging design. The challenge here was to change that from looking at emerging design to existing design, which gave us plenty of opportunity to involve real maintenance engineers working on real aircraft, which you clearly don't have in an emerging design. So the idea was to bring these people together. Now, the concept is to bring people together that don't necessarily always work together and give the OEM really raw exposure to what goes on the ramp and in the hangar. And that's the idea, is to bring together design engineers, systems people, accident investigators from within the OEM, technical directors from the operators, but most importantly, bringing experienced and novice maintenance engineers together to have a different conversation. And the first thing that we do is to really focus on the ground rules. As Scott said, it's an open conversation. And clearly what we want to do is break away from the traditional interactions. They're avoiding placing blame. This isn't about blame. Avoiding protection of reputations. Avoiding the failure to take on the problem, and actually just put things on the table and look at things. And that's the ground rules, that's the starting point. And in our experience, that is absolutely embraced. People really do engage with the process. So clearly, we're not going to be able to look at a whole aircraft. So what we do is we focus down on critical maintenance tasks on critical parts. So we spend time with the OEM to actually break it down and actually focus on what is critical, what do we want to be spending our time on. Now, clearly, the removal task isn't critical, so we eliminate removal tasks. We focus on the installation and servicing and inspection. But we focus them on the critical tasks, so the critical parts. And this is a requirement from 145. We need to focus on critical parts. So what do? Well, first of all, we start looking at the questions that we need to collect information on. So where is the task undertaken? What type of error can occur? And critically, all of the questions are directed at the experts in the room, who are the maintenance engineers, and not necessarily just the experienced engineer. The experienced engineer faces the norms that Scott was talking about, we always do it this way kind of approach, whereas the novice is able to speak out, well, why do you do it that way, and really question why it's done. And having the OEM there to actually say, what was the general assumption when you designed this task? And having that conversation about potential, what could go wrong, given organizational environmental constraints that possibly the OEM hadn't considered. So trying to bring that information together, and critically bringing on some work that Airbus helicopters did related to the contributing factors to error. So they'd done some analysis of errors that they were aware of, and said there were 5 key things that contributed to maintenance error. The first one was accessibility to the component. The second one was special tooling. Is any special tooling required? What is the perceived task frequency? Do you think that you're having to do this task a lot more than you would do, than was intended by the OEM? Is there a high demand on resource? So do you need a lot of people on board to actually do this task? All of which they found was contributing significantly to error. We also looked at past incidents, so not only incidents that were reported through MRs to EASA, but also collected within the organization, but picking up on the 80% of errors that are made by maintenance engineers corrected in the course of their job, and really trying to explore with operators what is going on, what is the work as done as opposed to the work that was imagined when the design was created and the task was written. So once we collect that, we look at the barriers that we already have in place. Clearly, the design incorporates an understanding of what could go wrong by the fact that if the component fails for whatever reason, from a technical failure, then there are barriers in place. So what is there to prevent the error? What can actually stop this error from happening at all? What is existing in the aircraft that reduces the magnitude? So do we, on a twin-engine aircraft, do we only maintain one engine at one check and the next engine on the next check? If you make a mistake, you're not going to make a mistake on both engines. What is there that reduces the error frequency? So what is it that makes sure that this doesn't happen? So reducing the exposure is one obvious way of doing that. So has the OEM already increased the maintenance interval to ensure that you don't have to maintain this as often? And critically, obviously, detection and recovery, where we look often to pick up maintenance errors. Is there anything within maintenance or flight ops that would identify this issue? And obviously, we're looking to action. Once we identify this, what are we going to do with it? And how are we going to choose the right barrier across the industry. This isn't just focused on OEM action, this can be operator action, it can be regulator action to resolve this issue. And that's the focus of the workshop, is to reach a point where we can actually make a difference. Now, we've already conducted 2 of these workshops, one on the 225 with Airbus helicopters and Heli-1 in Norway, which was hugely successful in identifying some of the things that we needed to do to modify the process. It was a pilot, but critically came out with really interesting things that Airbus have taken away. Short-term actions, including the modification of documentation, but medium and long-term actions in terms of research into some of these issues. And also, Airbus is doing some ergonomic analysis using virtual reality and mock-ups to actually understand what is the ergonomic burden of critical maintenance tasks on engineers. So there's some really useful work that's coming out of that first workshop. The second workshop was on AW139 with Leonardo, and we had a number of operators involved in that workshop. And again, we were able to look through some of the critical tasks and actually focus down on what really needed to change. And actually, a lot of the work that we do here is to show that so much of this is considered by the OEM. So there is a lot of human factors consideration within the design process. And we're working still on the final results of that workshop. Going back to Scott's example, so this is not necessarily about just meeting certification requirements. The aircraft already meets certification requirements. This is looking for opportunities to go beyond certification requirements to make a huge difference to safety. And we're not suggesting that this happens across the aircraft, but in critical areas. So some of the things that could be done in this example would be to introduce a new bolt design with a spring locking ring, so that should the bolt and split pin not be installed, then the nut wouldn't come out. You would retain the original locking features, but also could we introduce a sprung locking plate, again, to prevent the nut from coming out. Relatively low-cost, simple solutions that could be introduced that go beyond the certification requirements, but actually deal with the reality that maintenance engineers make mistakes. And when they make mistakes on critical components and the system doesn't pick it up, we have the potential for serious consequences. So we are partway through the process of doing this, and we've been working with the Heli Offshore members. We have new workshop plans. We're doing a H175 workshop in Aberdeen in January. We're in discussions with Sikorsky on S92 and Bell on the 525 to conduct further workshops going forward. We're also developing a standard, so making sure that this isn't a bespoke process for everyone. How do we standardize this so that we can apply it to any aircraft type for any mission? And also a design engineer training course, because what we want to do is we want to influence future design as well. We have courses planned for 2019, and we're looking at other things that we can do, including training courses for Part 145 to improve the maintenance human factors training that engineers already take. And also, as has been touched on by numerous speakers already, the usefulness of data in driving change. If we can collect more and better data related to maintenance errors, we'll have a much more focused approach on which ATA chapter to focus on, which areas of the aircraft do we need to spend more time on. So it's very much about trying to collect this data in one place. So we welcome your questions and comments in the questions and answers, and Scott and I will be around to answer any questions. Thank you very much.